the class. Right, so we are on the middle of the penultimate week, sorry, middle of the ultimate week of the school. And Professor Enrico Scalas is going to give the last lecture in the mini course, Monte Carlo simulations of anomalous random walks. Okay, Enrico, you're off.
Okay, thank you very much, Ian. And here I am. And yeah, this lecture today will be a bit harder probably than the previous ones because we are putting everything together, but also I am aware that you might not be familiar with some of the concepts we are going to discuss today. For this reason, I am also giving some further files to the organizers, including somehow a sort of document which could be considered somehow a lecture note for this course. Yes, so I forgot about that, but I discovered. So again, I hope you will be able to hear me throughout this session. And let me start by sharing the screen. And I would like to mention that the ideas that we have seen in this mini course are quite interesting also from the point of view the foundations of applied science, mathematical physics. Processes and differential equations, in particular partial differential equations of diffusion type in this kind of presentation. But this is crucial somehow in order to understand how these differential equations are emerging in applied science. So I would like to encourage you to, if you are particularly interested in foundational science, to keep an eye on probability theory and try to understand it better in the next years, because this is the key, in my opinion, the entry point. But of course, we are not discussing philosophy, so let me go back to the presentation and let me try to put this presentation full screen. And yesterday, we were essentially at this transparency where we were introducing the normal compound Poisson process after computing the Fourier Laplace transform and having the solution also of the problem of finding the one-point probability distribution of the continuous time random walk. So this is a particular continuous time random walk where the waiting times are exponentially distributed, independent and identically exponentially distributed, and the sum and the jumps are normally distributed with mean mu 0 and variance sigma square. If you want to simulate this process and check that this formula is working, you go back to this code here, which I will give to you later, and you just replace the variable distribution here with the exponential distribution. And then by plotting the histogram of x of t at a chosen t, you can compare that histogram with this exact formula here. Remember always that n equal to 0 has a delta function. So it will give you this spike in the origin that we have seen yesterday. Very good. So now, how can we connect this result to the diffusion equation? Okay, the connection is here. Now, if you remember, in one of the exercises that I was proposing you, I was asking you to see what happens when you are simulating the Poisson process and you send lambda to infinity, and you are simulating the Wiener process, sending actually a random walk with jumps that are normal, but then you send sigma squared to 0. Now, what we are doing is we are considering this limit, lambda to infinity, sigma squared to 0, which means that waiting times between events are with averages becoming smaller, smaller, and smaller. Remember that 1 over lambda would be the expectation of the waiting times if they are exponentially distributed. And the variance of the jumps is becoming also smaller, smaller, and smaller. So you are exactly doing this scaling limit that we have seen intuitively yesterday with the Monte Carlo simulation. But you do this assuming that the product lambda sigma square does not go to 0, does not diverge, but converges to 1. So there is this scaling here, which is an appropriate scaling, giving you the diffusion equation, essentially, or better, the solution of the diffusion equation. But let me see it. So what we can start doing is computing the characteristic function of x of t. And this is the Fourier transform of the previous formula. And the Fourier transform of the previous formula, again, you have all the convergences, series with positive terms, etc., etc. You just put the expectation inside the infinite sum, and you just compute the characteristic function of this object here. If you go into tables of characteristic functions, you see immediately, if you have a variance n sigma squared, that the characteristic function of this particular density is this one. So n times sigma square, and this is the absolute value of kappa to the square, and then divided by 2. Okay, but now this is equivalent to writing this, so lambda t exponential sigma square absolute value of k squared divided by 2 to the power of n divided by n factorial. And then this is, if you remember the series for the exponential, nothing else than the exponential of lambda t exponential of minus sigma squared k squared divided by 2. So you have the exponential of an exponential, if you like, but it is not a real problem. Then you use the property of the exponential function to get equation 6, which is the characteristic function of our 1-point distribution. That's beautiful. And now look at this. What happens if sigma square is small? That this term is small. So you can put here the first 2 terms of the expansion of the exponential, which will be 1 minus sigma square k square divided by 2, kappa square, actually, an absolute value of kappa square divided by 2. 1 minus 1 goes away, and you're left with just the linear term sigma square, absolute value of kappa square divided by 2, which means that if you do this limit with this scaling, because then you have lambda multiplied by sigma square converging to 1, this lambda sigma square goes to 1, and you're left with the exponential of minus value of kappa divided by 2. Number 7 is a characteristic function in itself. You have to use a technicality, Levy continuity theorem, which tells you that if the sequence of characteristic functions converges to something which is a characteristic function, then the sequence of random variables converges to the random variable with that particular characteristic function. And if you invert this, you get equation 8. And equation 8 is the solution of this problem here is the green function for the standard diffusion equation, the unique solution to the following initial value problem for the diffusion equation. So we have the connection. So this is essentially a proof of the central limit theorem for these random variables, in a sense. And this is the connection with the diffusion equation. And now, let's show that this characteristic function here is really the solution of this problem. Well, it is because if you take the Fourier transform of this equation, you get from a partial differential equation to an ordinary differential equation of relaxation type. And so remember that the characteristic function of the delta is 1. So you have this initial value problem for this ordinary differential equation. And here there should be a hat, sorry for that. And the solution of this, and the hat is missing here, is equation 11, which is magically inside the equation 7. This is really, then you invert this real space and you get ux. I'm sorry, this is coming every. Good. So now you have seen the main ideas that are behind this paper. My internet connection is unstable. Can you still hear me? Let me check. Yes, thank you very much. So let's hope that the internet connection is staying. What I wanted to say here, what are we doing? So we are considering a continuous time random walk where the waiting times have a distribution with this survivor function here, which is the Mittag-Leffler distribution that I am going to briefly introduce now. And the jumps are distributed according to another distribution, which is called the alpha stable distribution. And again, jumps and waiting times are independent from each other. So there is no dependence, even if we start with the formalism that allows dependence. So you look at this picture, which I am now magnifying. Look at the green here, yes, or the blue figure. So if you do this game of seeing the process from a distance or rescaling appropriately space and time, and I will show you what the appropriate scaling is in this case, you see that the process is no longer apparently, so this is a conjecture at this point, is no longer converging to standard Brownian motion or to Brownian motion. The Brownian limit is the red curve here, where the parameters are in the case in which you have normally distributed jumps and exponentially distributed waiting times. But if you consider, for instance, the blue case is with parameters that are not far from the parameters that give you the Wiener process, you see you have jumps, large jumps that do not disappear, and you have long waiting times because this function here, this is a log plot of the function. It's a survivor function, so it's starting from 1. But you see that for large times, it has a power law behavior. This is the power law behavior highlighted in the picture. And for short times, it behaves like a stretched exponential. So the behavior for short times is similar to the behavior of the variable, maybe even of the gamma. You cannot really differentiate empirically among these three distributions. But if you put the two things together, the important point is that you have these long tails here, meaning that the probability of having long waiting times is much higher than in the case of the exponential distribution. And in particular, here you have the stretched exponential, but an exponential distribution would go down like that. And therefore, for this reason, you see that you see these long waiting times where nothing happens, which survive the scaling. And then the jumps also are coming from a distribution with power law tails. And this is also giving you these large jumps, and they do not disappear when you take the limit. So we are going here towards other stable functions that are Bayesian of attraction for the continuous time random walk in the spatial part. And then because of the behavior of the waiting times, you also have these long waiting times. So you have some new somehow, well, it's not new now, but some new behavior, which is anomalous behavior with respect to standard diffusion. It turns out that this behavior is indeed captured, it's indeed captured by an equation that is called the space-time fractional diffusion equation, which we are going now to study. So briefly, what do we need to understand this process? So remember, we are always considering a continuous time random walks. So we have here a random sum of random variables. But now the counting process NT is different, is no longer the Poisson process. And also the process for the jumps, the random walk of the jumps is different, is no longer a Gaussian random variable, but technically a symmetric alpha stable random variable. But let's see first the time part. For the time part, we use a sequence of independent and identically distributed random variables with this complementary cumulative distribution function, this survivor function. Here there should be a u larger than 0, or I should put a t here, sorry for that. It is important that the parameter beta appearing here is between 0 and 1. Otherwise, this function takes negative values and becomes oscillating. And for beta larger than 1, it is defined, but it is no longer a legitimate complementary cumulative distribution function for a positive random variable. What is this function E beta? E beta of z is the so-called one-parameter Mittag-Leffler function, and it is defined by this formula here, which is one of the many possible generalizations of the exponential function. So if you put beta equal to 1, gamma of n plus 1 is n factorial. So you have the sum from 0 to infinity of zn divided n factorial, which is the exponential of z. But if beta is smaller than 1, this is no longer exponential. And if you replace z with minus t or minus u to the beta, you have here a minus t to the beta to the power of n that you have to compute. It is not very convenient to compute this function numerically, to use the series expansion in every region. But there is a trick. There are properties of this function, and it is possible to derive very fast algorithms to computing them. Now, one of the packages of R, which is called Mittag-Leffler, is dealing with these functions. It is a package written by Peter Straka, who was the author of the late Mark friend of mine and co-author, who unfortunately died last year. And it is ready for you to use if you want to reproduce our results. So we had to write everything from scratch in C++ for that paper, but now with R, you can really repeat what we did very easily with a few lines of R. So in particular, if you want to reproduce this picture, this figure, using that package, you will be able to do this very quickly. The package also has simulation of the Mittag-Leffler distribution. Let me share the screen again. And the simulation is, again, straightforward. Equation 20 in this paper gives you the formula to simulate Mittag-Leffler distributed random variables. What do? You compute two uniform random variables independently in 0, 1, and then you make this transformation where this gamma t is a scaling factor that we need here because we are doing this scaling of sending gamma to 0 in order to see what happens in that limit. But if you're not interested in the limit, you can set this to the value that you need for your application, or you set it to 1, for instance. You see, for there is this logarithm of u, and for beta equal to 1, this is 0. So you just have minus gamma t logarithm of u, which is exactly the formula that you use for the exponential distribution. So you see that there is a connection. And to prove that this is giving Mittag-Leffler distributed random variables, you can see technical papers in the probability and statistics literature. So let's go back to the presentation, and let us again put this full screen. The nice thing about the Mittag-Leffler function is that the Laplace transform for the survivor function and for the probability density function are known analytically. So you can use the method that we discussed yesterday to find the one-point distribution for the counting process, and it turns out to be given by a formula like this one, which generalized the formula for the Poisson distribution, where you have this t to the beta to the power of n divided by n factorial. And here you have this symbol, which means the nth derivative of the Mittag-Leffler function computed in minus t to the beta. So this is the one-point distribution of the counting process. And this counting process, as a renewal process, is called the fractional Poisson process. The name is here. So we have an analytical formula for the counting process distribution. And now the jumps. For the jumps, the situation is also straightforward. We use a symmetric alpha stable distribution, and its characteristic function is given by this formula here, with alpha in the interval 0, 2. If alpha is equal to 2, you recognize immediately apart from the factor of 2 and the sigma, also sigma squared divided by 2 set equal to 1, the characteristic function of the normal distribution. So for alpha equal to 2, you have normal, and for other values of alpha, you have a symmetric alpha stable distribution. So now, putting these two ingredients together, we can write the characteristic function analytically for the continuous time random walks with waiting times that follow the Mittag-Leffler distribution and jumps that are distributed according to the alpha stable distribution. Again, this is very nice. It is stable. You have this nice exponential. If you sum n of these random variables, you just get the exponential of minus n times the absolute value of k to the power of alpha, which is what I put here. And then you regroup again, and you get this formula here, which is the Taylor expansion of the right-hand side. So you are able to write this characteristic function in this form here, equation 12, which we are now using for scaling. For scaling, it's a bit more complicated, but it's exactly the same kind of reasoning that we have used previously. And you will recognize that for beta equal to 1 and alpha equal to 2, apart from some factors of sigma squared divided by 2, you have exactly the exponential of t, then multiplying x minus k squared minus 1. So it is exactly the same as before, and it leading to a diffusion equation with a different diffusion coefficient. Now, what we are doing, we are introducing two scaling factors. We rescale the jumps, and we rescale the waiting times, and then we let h and r vanish, but not independently, in a way that h to the alpha divided by r to the beta is equal to 1. By the way, these conditions using total total variation and slow varying functions, etc., can be relaxed a lot. But I put this here to simplify this condition here to simplify the proof. So it is true. This result, it is true also when the density of the jumps has power law tails, and when the waiting time distribution has power law tails as this one. So, but this is simplifying a lot our proof and also our calculation, and you can prove that you have again a weak convergence of the sequence of one-dimensional a function which is a green function of a equation. And now I will give you some hints on how to prove this result. And in particular, if you send HR0 under the hypothesis that this ratio here converges to 1, you start from the characteristic function, and then this is a continuous function, E beta, so you can put the limits inside, and this is converging to E beta. So again, you are doing as you were doing with the exponential, so you make h is becoming small. So this is becoming 1 minus absolute value of hk to the alpha. H is a positive number, so you can even take it out. H to the alpha, R to the beta appears here. 1 minus 1 goes away. And then you are left with the Mittag-Leffler function of 1 parameter beta computed in the point minus t to the beta absolute value of k to the alpha. And this is really the characteristic function as we will see now, of the fractional diffusion equation. So this is a way of solving the fractional diffusion equation, the initial value condition with initial value delta, so starting from 0. But let me say again that we need this Levy continuity theorem to complete the proof and say that this limit is true also for this. And maybe here I should have, I think I will have to tweak a bit this presentation because here it should be PHR. Yes, so with subscript HR, just to be more precise. However,
Sorry, we can't hear you anymore.
So where did you lose me?
About like a few seconds ago. We can hear you now.
Okay, thank you. Thank you very much. So
No worries.
first of all, let me see if there is any other question. No sound. Okay, sorry. Now you can hear me. Yes. So
Yes.
and so what I wanted to say is that this function, whose Laplace, whose Fourier transform we obtained here, is the solution of this problem. And now we have to say something about this problem. What is this problem? So I have not put the definition of the operators in the presentation, but you find the definition of the operators in the paper. Sorry. So what is the Caputo derivative? What is the fractional Laplacian? First of all, the fractional Laplacian is an operator with symbol minus k to the alpha. So the Fourier transform of this derivative here is minus k to the alpha Fourier transform of the function f, the function in the domain of the operator. It is possible to write the operator in an explicit form, equation 14, where you see that you would need to know values of the function far away from the point where you are interested in this derivative. Yes, so you have this sort of convolution integral with this power law kernel. And the Caputo derivative is behaving in the same way. It is given by equation 16, and it has Laplace transform given by equation 50. So if you put everything together, you have all the tools to solve the this problem, which, going back to the presentation, I am going to do now. If I take the Fourier transform of this equation here and of the initial condition, I get this equation 14, this problem, which becomes a problem for the Caputo derivative only. So you get rid essentially of the fractional Laplacian, which is replaced by its symbol. I think I also have to change the notation for this derivative to be consistent with the paper, which I will do. It turns out that this problem for the Caputo derivative is well posed and has this unique solution here, equation 15, which is in fact exactly what we were expecting here. Now, let's go back to the paper for a while, and let me see, there is maybe a question. Ah, no, no question. So, yes, going back to the paper, I wanted to show you some of the results briefly. So it's section 4, numerical results. So for instance, this figure here shows the convergence of the solution okay, there is a rescaling of the solution, but that's fine. As we are making gamma t smaller and smaller. Remember that we used this relationship, gamma x equal gamma t, to be beta divided by alpha. And in the presentation, I was calling gamma x equal to h and gamma t equal to r. So there is just a change of notation. And let us see a bit, for instance, let's consider one of these cases. So this is the case that we have seen in the previous, in the first part of the presentation today. So the case in which alpha is equal to 2 and beta equal to 1. So you have normal jump and exponential wave. So let me magnify it. Like that, it is fine. I'm rescaling a bit the variables to show the convergence. So the purple one is the solution to the continuous time random wall equation, fully discrete yet, with gamma t equal to 1.4. And you can appreciate this peak here. And then this peak is becoming smaller and smaller as I increase gamma. It is always there. I decrease gamma, sorry. It is always there. Remember, decreasing gamma means also decreasing gamma t, decreasing also gamma x. Yes, so, and the function u alpha beta that you have seen is this solid line here, the black solid line. And you see that this color here for which I do not have a name, maybe cyan, I don't know, it is already superimposed to the theoretical solution. There will be a small bump here in the origin that you cannot appreciate anymore for gamma t equals 0.01. Okay, so this shows this function here, apart from the factor 2 that is appearing here, maybe. And coming back to, for instance, this case here, alpha 1.7 and beta 0.8, here you have jumps, both in waiting times and which appear then as plateaus in the limiting process, and also jumps in the position. And the function that you are approximating is this line here. And now we need to go to very small gamma to approximate it correctly, but it is there, yes? And you see also how these functions are approaching more and more the solution as gamma t becomes smaller and smaller. And you see also the different behavior because you have this cusp here, which was not there in the case of the Gaussian, and the cusp is appearing only in the limit. And this is even more extreme with alpha equal to 1 and beta equal to 0.9 with a very high cusp. And then of course, as in all numerical analysis papers, we were studying the convergence to the exact solution of this method, so the Monte Carlo simulation for different values of the parameters, and this is shown here. So this is the scaling parameter becoming smaller and smaller as you go from right to left, and this is the distance between these two functions also becoming smaller and smaller as you reach 0.001. And then at the beginning, this is quite a steep convergence, and then it becomes much slower. I mean, not being numerical analysts, we stopped here in this paper. But normally, if you are a numerical analyst, you would try to do more in this direction and check which is the order of if you can find theorems or converge of methods. Of course, this is a Monte Carlo. It is possible to deal with probabilistic results and check. I mean, always the convergence of Monte Carlo simulations is a very interesting problem technically and not necessarily easy to solve. The rule of the thumb is that Monte Carlo estimates are a good as good as 1 over square root of the number of samples. So here you would have a convergence which is related to this parameter, but also to the sample size. By increasing sample sizes in your histogram, you might have a better result. And we have not studied this here. Very well. So what else can be said? One thing. Yeah, I see maybe there is a question. Okay. So my description of the paper and of the final results. Yeah, I don't see any message, so I guess you could hear it. And now let me conclude. With this transparency. So we were at this convergence. We have seen that there is a connection between this continuous time random walk and the solution of this this is a pseudo differential equation with non-local operators. We have scratched the surface of functional convergence. But if you want to know me more, you can contact me at my email address, which is here, and I will share this presentation after correcting some typos later today. And I would want to thank you for your kind attention. And also, it's a very good opportunity for me to thank the organizer for their kind invitation and for giving me the opportunity of presenting these results to you. Hopefully you will get interested in modern probability theory, and at least some of you, and its results, and maybe we will meet in the future in some conference, who knows. Thank you very much, really. So I leave it to Ian to conclude, and maybe there are questions and so on.